and welcome to the first day of lecture of Math 1093 Pre-Cal. So we're going to start out with, in chapter 1, there's review material. It's that material that the teachers like to say, you should already know this. And don't you just love those teachers? Yeah, me too. I don't expect for you to remember all of this, and so that's why I like to cover it. Again, it's just review material, and I kind of pull the things out that I know you're going to need later. When we get to them later in the class, I'll kind of do a short review again, or more of like reminders. I won't spend this much time on them. So again, don't forget about your class handout so you can jot notes down. Kind of the nice part is a lot of times students in class will say, Cindy, you go too fast. Well, doesn't matter to you guys, hit pause, right? So you kind of have that nice part to be able to pause through these. All right, so the first thing we're going to talk about is distance and midpoint formulas. So this is section 1. So if you're given a point to begin with, and it says which quadrant is this point in? So we're going to first look at the rectangular coordinate system. And if you remember how to plot, so you draw your x, y axis, and the very first value is your x, which is negative, so you go over that way, right? And then your y is negative, so you go down that way. Then if I actually plot this, I go over there, I go over there. And if you remember where we labeled quadrants, 1, 2, 3, 4, this would be in quadrant 3. This is actually very important, as you're going to see later in this course, as we deal with what quadrant we're in depends on certain things that we can do. So be sure you remember your quadrants and plotting points. The distance formula, if I look here, which one of these might be the correct distance formula? That one. It's kind of easy in a way for me to remember because I know I'm subtracting the x's. In other words, I'm taking, let's say this was 5 and this was 4, then the distance from 4 to 5 would be 1. How do you get it? You subtract them. So that's kind of how I always remember that. And so then you're squaring the difference of the distance of the y's, adding them together, and then square rooting. So if I want to find the distance between the 0.13 and 5.6, I had a teacher a long time ago say, draw a picture, draw a picture, draw a picture. I think it makes sense because it tells me I'm looking for that value. If I'm looking for that value, and many of you probably remember the wonderful Pythagorean theorem, is so if I'm looking here at the distance, what I'm looking for is this pink line, that distance. How I find it is I find the distance of my x's and the distance of my y's. And that's what I said, do you recognize this formula? That's your Pythagorean theorem. But I find this distance here, and then this distance, and of course squaring both of them. And that's my Pythagorean theorem. So it's kind of nice. You can see that a lot of times these formulas go together with each other. And so then finally, don't forget to square root it because this was squared, and actually solve for d, then I need to take the square root and I get my answer, which again, some of you may have recognized this is a 3, 4, 5, one of those neat little triangles. Midpoint formula, which of the following is the correct form for the midpoint formula? This one you're adding together the distances and then dividing by 2. You're cutting it in half, getting the midpoint. Again, let's go through an example. If I want to find the midpoint between these 2 points, then I simply plug in my x's, I add them, divide by 2. I plug in my y's, I add them and divide by 2. So this point here would be the midpoint between those 2 points. All right, the distance of a moving object, a hot air balloon headed due east at an average speed of 15 miles per hour and at a constant altitude of 100 feet passes over an intersection. Find an expression. So an expression, just something you could set up with distance d. So, hey, sounds like I'm going to use the distance formula. From the balloon to the intersection t seconds later. So when I read a word problem, I'm just like you. I'm going, there's too many words. So I kind of go through and see the information that's going to be useful to me. Okay, and I highlight that information. And now from here, I can actually write out my distance formula. So I'm going to leave that one up to you to see in your notes if you can write that out for me. So you know you're going to start with the distance formula, and then you're going to have to figure out what to plug in for the values. And I'll check in with you to see how you did on that, writing that out. All right, so that was distance, midpoint, all that good stuff. This next section is graphs of equations in two variables. So that's your rectangular coordinate system, and so important, circles. You know why it's so important? If you look at your textbook, see the textbook? It says a unit circle approach. This whole class is about circles. So you really need to remember about circles. So the first part, determining whether a point is on the graph of an equation. So is 0, 4 on this graph? Well, you could either just plot this line and see if they actually fall on this line. Okay, so I can see 0, 4, doesn't look like it. -1, 3 does, and -2, 0 does. Or I could plug these values for x. I could plug in a 0 and I could plug in a 4 for y into the equation, and I would see that 0 plus 4 does not equal 6, so that one didn't work. Okay, so that's two ways you can kind of tell if points are actually on a line. What are the x-intercepts of the graph? Remember, the x-intercepts are where you touch. You don't always have to cross like this one, where you touch the x-axis. Where are the y-intercepts? Where you touch the y-axis. So would be those actual points. Find the x-intercepts and the y-intercepts of the graph of y equals x squared minus 4, and then graph by plotting points. So when you're finding intercepts, so for example, if I want to know what value makes this equation equal to 0, I can set it equal to 0, which I did, and I can solve this and I can find the two x values for my x-intercept. So in other words, I let y equal 0. So when y equals 0, that's an x-intercept. I have an equation here I can solve. I factored. I noticed that was the difference of two squares, and I solved it. Now, I want to remind you, some of you may not solve this left-hand side, and I'm not one of those that you got to solve it my way or the highway, right? You can solve these any way you want to solve them. The right-hand side is a little easier because I moved the 4 over there. If you remember, when you square root, you have to do plus or minus. See, remember these answers were 2 and -2. So do not forget that. When you square root, you have to plus or minus. I think that gets lost and forgotten because a lot of times when you do word problems, you only care about the positive value. And so that's my thinking of why that gets lost a lot. I think the kitty's going to make another appearance in this film. Okay, so in other words, my x-intercepts then are a point, so 2, 0, and -2, 0. If I want to find the y-intercepts, those are typically a little easier because you're not really solving, you're just plugging in 0 and the x goes away, and that gives you your y. And so your y-intercept would be 0, -4. All right, and then of course it says use points to graph. Typically when I hand graph, we don't do a lot of that anymore with technology, but I typically try to pick some negative values, some positive values. Later in this introduction thing, if you remember transformations, you may not even needed that because you know what x squared looks like, the graph of x squared. But this would just be one way of finding actual plotting by points, and then I can plot my points. Okay, but again, if you kind of remember the transformation, x squared looked like this parabola, and then I brought it down 1, 2, 3, 4 units. Symmetry. Symmetry has to do with anytime I think of symmetry, they always talk about somebody that's very good looking is symmetrical. In other words, they don't have, if you cut their face down the middle, the right side looks just like the left side. They don't have like this one big fuzzy eyebrow and then this one eyebrow shaved off, weird stuff like that. I don't know. I just come up with this stuff. But when we talk about functions being symmetrical, that means if you cut them in half, the left-hand side looks like the right-hand side. You can certainly have cutting it vertically or horizontally. So if I'm looking at points that are symmetric, so if a graph is symmetric with respect to the x-axis, soon as I see that, I think of the x-axis being my mirror, and I have this point 3, 2, then what other point would be on the graph? Well, then I would just mirror and bring the point down here, and I would see my x value is still the same, but then my y value becomes -2. If I'm looking at the y-axis, so that's my mirror, then symmetric would be on the other side. Again, my y value would stay the same, but my x value becomes the -x. If it's with respect to the origin, so there's kind of a mirror right here, I'm going to jump down to this other side. And if you can see what happened when it was symmetric with the x-axis, your x stayed the same, but your y went negative. When you were symmetric with the y-axis, your y stayed the same, but the x went negative. When you're symmetric with the origin, both values go negative. That's a good thing to remember, so don't forget it. Okay, if we want to talk about the standard form of a circle. So this is the formula. So it says, write the standard form of the equation of the circle with radius 4 and center 2, -4. The HK is your center, and then R, of course, is your radius. So looking down here, if I'm matching this, my 2 is positive, so I'm just putting a 2 in there. So I know the answer is B or C. Here, when I plug in a -4 into this formula, a negative and a negative becomes positive, and so I get a +4. And then, of course, my radius being 4, 4 squared would give me 16. If I want to take, if I'm given, this is a different example, and I want to graph this, remembering that my center is my HK, but remember the form here. So if this is positive, then my H must be negative, negative and a negative. This is negative, so that just stays the same. So HK is the center, -3, 2. My radius then would be 4. So as you can see, I count 1, 2, 3, 4. I put a point. Go up, 1, 2, 3, 4, put a point, go down, 4, put a point, go left, put a point. And then you got into actual functions. So when we talked about functions, we said that the big deal with a function is you can't have one x going into two different y values. Okay, so one input can't have two different outputs. And that kind of says this here, where we call the x values our domain, our y values our range. So a function from x to y is a relation that associates with each element of x exactly one element of y. So you could have two x's going into one y, but you can't have one x going into two different y's. In other words, let's say the domain is my students' names, and then the range is your social security number. Well, you can't have two social security numbers, right? Unless you're like in the witness protection program or something, I don't know. So once again, going back here, we can see that definitely this does not represent a function. As I mentioned earlier, the x values are the domain, the y values are the range. So just like in algebra, we're going to have functions, trig functions later, and we're going to have to understand domains and range. So if the domain are the x values, I look here and I see, I have two x values going in, or the same x value going into two different ranges. So this is not even a function. So you got to be careful of that. If I look here, find the domain. So the domain are the x values, -2, 4, 3, 2. Well, it didn't look like all of them are being listed, so I just look here and I see, well, certainly 1 is not an x value. -2 and 3 is, but then looking at the ranges, I need to make sure that the y values matches. And so I see that I have -2 is an actual range and 3 is an actual range. If I want to evaluate a function, I always ask students, what does f of 3 mean? And you're very good at this. You say you just plug it in. That's what you do. You just simply plug in a 3. So I take -3 times 3 squared. So 3 squared would be 9. 9 times -3, -27. And then I'm going to plug my 3 in here. So I'm going to have 2 times 3, 6. So I have my -27 plus 6, which shows all down here. And I get my answer. So again, you're going to deal with functions in this class just like you have in algebra. There'll be different looking functions, but you'll still do the same thing when we say evaluate the function. All right, find the domain of the function. No clue what to do. Well, we got to go back and we have to remember what domain means. The only time you have to worry about domains is if you're dividing by 0, taking the square root of a negative number, things like that. And so if I do not want to divide 0, so I need to figure out what numbers would make the denominator 0. And what I actually did is I factored the denominator. Factoring, going to come back and haunt you, huh? I factored this denominator into x plus 1 and x minus 3. And then I set both factors equal to 0. So x would be -1, x would be 3, to see what makes the denominator equal to 0. And that's how I found my domain is any number in the world except for those two numbers. Different properties of functions. We have the even and odd functions. A function is even if you plug in a -x and you get the function back. So for an even function, for every point xy on the graph, the point -xy is also on the graph. And then odd, when you plug in a -x, you get a -f of x. So in other words, your y. Remember, f of x is just your y value. So when you plug in a -x, you actually get a -y. So it says a function is even if and only if its graph is symmetric with respect to the y-axis. So going back here, if you remember, we said when you were looking at symmetric, and you kind of see with the picture here with the y-axis, what happened is my x became negative, but my y stayed the same. If I'm looking at here, it says a function is odd if and only if it's symmetric with the origin. If you remember that when we talked about being symmetric, if you plug in a -x, you should get a -y. So in other words, your positive xy became -x and y. How do I tell if a function's even or odd? Well, again, I kind of look at to see if what they're symmetric with. This is definitely even because I can see it's symmetric with the y-axis. This last one is symmetric with the origin. This, there's no mirror. In other words, I can't say the exact same values, x values or -x values are going to be the same on both sides. How do you determine whether a function is even or odd without graphing it? You replace x by -x. Remember the definitions. You always come back to the definitions. So if I plug in where I see an x, I plug in a -x. So I plug in a -x. -x cubed is still -x, right? Because it's -x times -x, which is positive, and then times another -x, which becomes negative. Here I have a negative and a negative. If I factor out a negative, so that becomes positive, that becomes negative. Notice this looks exactly like my original function, but with a negative. So it's the negative of my original function. That's what this definition is saying. If I plug in a -x, and I get my original function back, but the negative of it, then it's an odd function. All right, determining whether a function is increasing or decreasing. I can certainly see that the function is increasing from -4 to 0. So you typically will see it written like that, or even in interval notation. I can see where is the function decreasing. It's decreasing from -6 to -4. And then it's also decreasing from 3 to 6. Okay, so just seeing where functions, by looking at a graph, where are they increasing and where are they decreasing? Where is the function constant? Well, as I can see, it's constant between 0 and 3. Then we look at finding maxes and mins. A local max, in other words, they're easy to find right with parabolas, but all they really are is the highest point of the function. This function's not going to turn and go back up. If we're looking at minimums, and we're looking at within an interval, that's why I'm using the word local, then we end up with the lowest point within that interval. Average rate of change. This is something you will come back to if you're taking calculus. So you might put a little note. Cindy said, this is the very first thing they teach you in calculus. So let's look at this, the average rate of change. Change of y over change in x. I remember that, that's slope. So that's all this is. It's called the average rate of change, it's called the difference quotient, but that's all it is the slope. If I want to find the slope of a secant line, what's a secant line? If I have a function, that's this blue, and I connect two dots anywhere, okay, any 2 points on this function, and I draw a line, that's a secant line. So secant line could be anywhere. These are just the 2 points I picked, was this point C, and then this at X. So I could find the slope, the average rate of change of this little curve right here. Well, as you see what you're finding the slope of the secant line. But it gives you on average how this function is changing from C to X. So let's try to do this. Find the average rate of change of this function from 1 to 3. So looking back at the formula, you see what we're doing. We evaluate the y value, if you want to say that, the f of x, minus the other y value. Well, guess what that is? The top, the change in y's. And then we divide by, we're evaluating the x values. So going back here, to evaluate my y values, I evaluated 3, the larger one, minus 1, the smaller one. So look at this line. This is 3x squared minus 3x squared. This is my y2, if you want to call it, and my y1. And then I divide by the difference in my x values. So once I've plugged in my function to get my y's, and then I plug in the values to get my x, I divide and I get 12. So what the 12 means, it is the slope of this function between those 2 points. So remember, this is the slope of the secant line. How can you find the equation of the secant line? If you remember, if you have a point or 2 points, if you have 2 points, you can find the slope, and then you can actually plug in your points. So what we just found was the slope. So that average rate of change, what we just found was the slope, so that was 12. Then I could pick either point. So let's say I pick the one with the x, so my x value would be 1, 3. Okay, how in the world I get 3? I go back to my original function, I plug in 1, and that gives me my y value. So I plug everything in, I solve for y, and I get my slope intercept, my y equals mx plus b, and that gives me something I can actually graph. And I'm going to graph this and plug in my 2 points just to ensure that they're actually on the graph. All right, that's a good stopping place. That's a lot of material, right? So I'm going to stop right there, and I'll finish up the review in the next lecture, but go through all of this slowly. Okay, I know I'm just going bam, 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 but you can slow it down. Go through all this slowly and contact me if you have any questions on anything, because all this review material you're going to need later in the course. All right, see you next lecture.